You know, my clock's good. You must have you probably have really slow internet, Austin. So yours didn't start up till 11:31. I don't know what you want me to tell you, buddy. You can calm down too, Abby. Hey, how's Costa Rica, by the way? Did you actually end up going there? Or with all the craziness that happened, did you guys not go? Squad stream. Yeah, I don't think so. Nice, still win after all. Okay, cool, cool. Well, hope it was a good time. All right. So let's go ahead and do this. So we have our couple different ways of solving equations that we've talked about so far, exponentials. So number one is what we talked about last time. And it is just a single exponential that we have here. So I just want to isolate that exponential before I do anything. So I'm going to add 13 to both sides. 24. Oops, plus 2. Now, right now I have an exponential where the 5x plus 2 is trapped up in the exponent. And so I need to get rid of that base 3 somehow. So in order to get rid of exponentials, we use their inverses, which is logarithm. So I do log base 3 on both sides. Right? Always do the same thing to both sides. And we choose 3 because that was the base that we had for the exponential. So that's the base that we want to use for the logarithms as well. That's great for us. Log base 3 and exponential base 3, they cancel each other out. So all we have left is 5x plus 2 equals, so I asked myself 3, do I know 3 to what power makes 24? Now don't get confused because I know that 3 times 8 is 24, but that's not a power. That's not an exponent. So I don't know. 3 to the what power makes 24, some decimal, some fraction. So I'm not worried about doing it in my head. And now it's just a matter of solving. So subtract 2 and divide 5. Minus 2, and then divide both sides by 5. So this should be my final answer. Austin, you did an internet speed test. 203 download, 224 upload, and that's not bad, but you gotta get that full 1,000, man. That's where we're living right now. You could still be much faster. Anyways, I thought you'd just be happy that I'd be rocking this today, you know? I'm trying to do you a favor here. For number 2, so this is one where I have exponential on both sides, and I'm going to try to get the bases to match because I think I can do that. So we have to think about 49 and 343, what they are powers of, if they're both powers of something, and they are. They are both powers of 7. So So 343 I can rewrite as 7 cubed. 1 over 49 I can write as 7 to the power of negative 2. Right? Because 7 squared makes 49, but the negative is what drops it down then into the denominator. Power of power. So distribute 8x minus 10. 6 minus 9x. Once we have the bases that are equal to each other, we just set those. 8x minus 10 equals 6 minus 9x. Subtract 8x from both sides. Or I guess add 9x to both sides. It doesn't matter which side you bring the x's to. Subtract the 6 from both sides. And then lastly, divide by negative 17. So x equals 16/17, because those negatives will cancel each other out when we divide. Not going to comment on how I'm wearing it. What do you mean? What's wrong with this? We're in 2020 quarantine fashion now. Okay, there are no rules as to how we wear ties, or it's just we're just figuring it all out as we go. So I don't want to hear it about how I'm wearing it either. So we're gonna delve into some word problems here. It would be super awesome if you had your graphing calculator with you while we do this. Okay, I'll pull one up on the screen as well. But definitely going to need a graphing calculator, because a lot of times the stuff that people mess up on is just typing in the values and making sure we do that correctly in our calculator. So pull that up, go grab it so that you can do it along with everyone. All right, so we're going to talk about growth and decay. And one of the most common forms of exponential growth, is compound interest. These are super common problems. You see these show up on like the ACT and like various like standard like end of course exams and various standardized tests like that a bunch. There'll be a question every now and then. So the compound interest formula is this. This should be something you saw before in Algebra 2, where that capital P just represents the principal amount, so the starting amount of money that you had. R is the interest rate. Now we have to make sure that whenever we use it in our equation, it's a decimal. N is how many times that interest is compounded in a year. So we'll talk about different amounts that we compound. And then T is the time in years. All right. So hopefully this formula is relatively familiar. So we'll just do a couple quick things with it. It's not too difficult to do. It's just a lot of plugging in numbers and then making sure we type it into our calculators correctly. So for example, let's calculate some compound interest. So let's say we start with $7,300 and it's compounded semi-annually at 7% for 3 years. All right, so a good idea for all of these problems is let's just write out the information we know and kind of label it. That way we know exactly how to plug things in. So the capital P in this case is 7,300 because that's how much we started with. R, the interest rate, is 7%, but I don't want to use 7, right, because we want to use it as a decimal in our equation. So 0.07. It's compounded semi-annually. Okay, so N represents how many times it's compounded in a year. So semi-annually would mean twice a year, 2 times a year. So just my general formula would be, oops. Sorry, let me fix something real quick. A of t equals 7,300, 1 plus 0.07 over 2 to the power of 2 times t. Right, this would be the formula we would use to determine how much money do we have after any amount of time. But we don't want to know just for any amount of time. We don't just want to know the formula. We want to know how much will I have specifically after 3 years. Okay, so let's just take our formula and plug in 3. All that stays the same. So the only difference now is in that exponent, I have 2 times 3. So this is what I'm going to bring up my calculator here. Make sure when we're doing these problems, all these growth and decay problems, that you are calculating as few times as possible on your calculator. Okay. The full formula again, like the original. This. Okay. Just let me know when you're good. Okay, yes, thanks. Okay. So all of this that I've circled in that dotted line, I want you to type in that entire thing to your calculator at once. Don't do it like line by line where you first type in 0.07 divided by 2, and then you do +1, and then you do to the power of, and then you do times. Type in that whole thing together. That way you don't mess up. So let me show you how this should work. So So 7300 parentheses 1 plus. Hopefully you know that on your calculators you can make a fraction. So alpha, if you click alpha y equals, it should bring up a screen that looks like this. And we want to click this first one. So you can just hit enter or 1. So it'll make an actual fraction. That's very helpful so that you don't have to worry about doing parentheses. So 0.07 divided by 2, parentheses, to the power of 2 times 3, which I know is 6. Don't ask me how I know that. I just do. All right, so this is what I'm saying. We want all this typed in one line together. Okay, don't be hitting enter a lot. You should only have to hit enter once for these problems. 8973.56. So Abby asks, what decimal place are you round to? For these problems, since we're talking about money, then we will round to 2 decimal places. Now We'll round differently otherwise, but if we're talking about money, then it makes sense that we round to 2 decimal places, since that's just as many as we use for cash. For number 2, or the second example, $2,100 at 13.6% compounded quarterly for 4 years. All right, so let me just list out my information again. P is 21,000. R 0.136. I'm frozen. Can anyone confirm? I don't know. For me, okay. Yeah, for me, it says I'm still good. Classic Lewis, man. And quarterly, compounded quarterly. So that's 4 times a year. Well, Austin, I thought you and Lewis were quarantining together so that you guys could still hang out. Right? And we want to know for 4 years. So 21,000. 1 plus 0.136 divided by 4 to the power of 4 times 4. So notice that this 4 in my exponent comes from the n. However, this 4 comes from, that's how many, that's the t that we want to know how many is it, okay, after how many years. So I know that they're both 4s, so it's a little confusing, but those 4s come from different places. One of them is the n, and one of them is t, because we want to know for 4 years. And then same thing, we want to type all this in at once. Oops. So 21,000. Oops. Nope. Parentheses 1 plus. Make an actual fraction so you don't have to worry about doing parentheses for dividing. So alpha y equals, and then 1. So it actually makes the numerator and denominator 0.136 divided by 4 to the power of 4 times 4, 16. Enter. Equals, again, since we're dealing with money, we'll round it to 2 decimal places. 35,854 and 85 cents. So please do that in your calculations, because otherwise you'll get slightly different answers than me probably if you're like rounding at every step and hitting enter a lot on the calculator. Just type it all in at once and hit enter once and you'll be good to go. For this third question, $3,000 at 6 point. This is the same thing. The one thing I will comment quickly on is weekly. Nobody ever knows how many weeks there are in a year. I had a student earlier in the year guess, I don't know, 200, and so that's pretty close. But yes, Aiden, exactly. Weekly is 52. All right, 52 weeks in a year, 365 days in a year. Okay, so just wanted to mention that. 50. Right, so we would do the same calculation. But that's boring. That's stuff we already know. Let's go on to a slightly different format of problem. Right, this is where we start to get to the good stuff. In talking about continuous growth and decay. So the formula like we use for compound interest is because we're talking about, because that always has a problem of, or the question is part of it that's like compounded daily, compounded weekly, compounded minute by the minute, or whatever. Well, what if it's not each something like that? Let's just say it's always compounding, continuously compounding. Well, then we use this formula right here. So this a sub 0, or a0, is the initial amount. K is the growth or decay rate. Right, depending on which we're talking about, it could be the rate that's growing, the rate that it's decaying. And again, we want it to be a decimal. Is it also called PERT? Oh, I know what you're talking about. Yeah, for compound interest, right? You've probably sort of seen this formula before when you talk about compound interest, or specifically for continuous compound interest, then yeah, I think it's usually written like this: P times e to the power of RT. Yeah, because the P represents principal amount of money, R represents the rate. So yeah, it's basically the same thing, except we're going to use this formula for, since we're not just going to use it for interest, we're going to use it for other stuff. Then we'll use these variables. But yeah, it's that same thing, Abby. Good connection. And T is the time. And the cool thing about this formula, one of the cool things, is this time could be any unit. For the compound interest formula, T has to be in years. That whole equation is based on T being the amount of years. However, in this formula, T could be anything. It could be years, it could be minutes, it could be seconds, it could be billions of years, it could be a nanosecond, whatever. All right? T could be anything. And then just another quick last note. If we're talking about growth, then K will be positive. If we're talking about decay, so something that's decreasing, then K will be negative. So this will be something to keep in mind that we might need to keep track of, because a problem might tell us a decay rate, so we need to know in our equation that should be negative. Right? So just keep that in mind. That's how we'll know if we're looking at an equation, if it's growing or decaying. PERT. All right, so solving some word problems. So let's say there is a population of bacteria that grows 17.4% per day. There's 20 million at the start, how much will there be after 15 days? Okay. So again, first things first, just label your stuff that you know from the problem. Don't try to look at the problem and immediately plug and play stuff. I mean, you can if you get really good at it and you feel confident, that's great. But my experience is that even when you are really good and really comfortable with this stuff, it's still easy to every now and then slip up and mislabel or misplug in a number where it needs to go. Right? So it grows 17.4% per day. Okay, so my K should be 0.174. And I know it should be positive because it's growing. So I don't need to worry about negatives. It's growing, so it should be a positive rate of decay. A0, which just stands for the initial amount. How much is there at the start? Well, we know there's 20 million. So I'm going to put 20 here. I'm not going to write out 20 million. I can just use million as like my units. So as long as I keep track of that, and then at the end, when it says how much will there be, as long as I say the number I get and then million bacteria, then it's still okay. And the question is, how much will there be after 15 days? Well, like we did before, let me first just write out my general equation, which is this. So without even plugging in anything for T, this is my equation that I'll use for this bacteria's growth. So now, since I want to know, hey, how much will there be after 15 days? Then we'll plug in 15. It's kind of ugly. .174 times 15. So I'll bring up the good old calculator. And again, plug it all in one go. 20 E. Usually E is behind the ln, so you'll have to do second ln. Typically, if you have a TI-84, almost definitely. E to the power of 0.174 times 15. Enter. 271.981. Okay, so for these problems, so before, when we're talking about money, great, let's do 2 decimal places. For all of these problems, other problems that we do for growth and decay, we're going to do 3 decimal places. Okay. All right, that'll just be our standard that we go off of. Let's round to the thousandths. 3 decimal places. So 0.981. 0.981 what? Million bacteria after 15 days. A lot of bacteria. Oddly topical. Can we say 271,981,017? So Matthew, you can say that, but if you wanted to write that out as your answer, so 271,981, then your units that you would put on it is just bacteria. because you're already writing out the millions. You're already saying, you know, this number tells me 271 million. So I don't need to also write million bacteria after that. We do need to write the million here because we're writing it in a different way. Okay. But yeah, sure. You're free to do that. I just don't want to write out all those numbers because I'm lazy. Okay, let's go to our next one. So carbon 14, oops. Carbon 14 decays at a rate of 12.3% per 1,000 years. Wait a minute. Oh, there we go. The current mass is 322 milligrams. How long will it take for it to decay to 100 milligrams? All right, so let's just write out our information. So this decays at a rate 12.3%. So I don't want to write the percent. Let's write it as a decimal. Now, the other thing that's super important, this is talking about decaying. So that means when we write our it's not R. Why am I saying that? K. Sorry, we use K now. So that K, that rate, should be negative. All right, that's something that you have to identify and make sure that you put the negative. All right, so just based on the fact that it is decaying, we will put the negative sign on our rate. All right, don't forget it, because otherwise you'll mess up your whole equation. Right, current mass is 322. So A0, 322 milligrams. And we want to know how long will it take for it to decay to 100? Okay, so the thing I'm trying to find is how much time will it take to get to 100? I like writing that part too, just to kind of give myself an idea of this is my goal. Figure out what is that question mark supposed to be? How much time will it take to reach 100? So I'll first set up my general equation. 322 E negative 0.123 times T. So the only thing I've plugged in is the A0 and the K. I'm not worried about T or anything right now. All right, so this equation's a little bit different in that I want to figure out what is T. How much time will it take to reach 100? So I'm not going to plug in 100. Right? That is a different type of question. Right? If the question asks me how much will be left after 1,000 or 100,000 years, then yeah, I'd plug in 100. And that would tell me how much is left after that amount of time. But that's not what the question's asking me. It's asking how long will it take to reach 100 milligrams? So I'm going to do this slightly differently. So I'm going to write this again. I want to figure out if this equation is going to reach 100, how much time will that take? So I want to solve for T, finding time. So this is now exactly like, this is why we did those solving exponential equations before, right? So first, I'm going to divide 322. So 100 divided by 322. Oops, forgot my T. we want to get rid of the exponential base e, right? So remember, to get rid of exponentials, we need to use logarithms. And specifically, a logarithm base e is natural log. So we'll do natural log of both sides. Keep forgetting t. And so since I have the natural logarithm, which is base e, and I have the exponential, which is base e, those cancel, just like we did yesterday and on the warm-up. So I'm here. And then lastly, to solve for t, I just want to divide by negative 0.123. So this is how I should be able to get my answer. But let me pull up my calculator. So just like with our last problems, we want to type all of this in together. Don't do it one step at a time. All right, just type it all in. So I'm going to first create a fraction. So alpha y equals 1. So in the numerator is my natural log. I'm going to do another fraction. Alpha y equals 1. So 100 divided by 322. Close parentheses. And then in the denominator, negative 0.123. Make sure you use the negative symbol, not the minus sign, right? If you mix up using your negatives and minus, your negative symbol and your minus sign, your calculator will freak out about it sometimes. It does not mean the same thing to them. So the negative sign is that very bottom button, almost in the middle, right? The minus sign is the one that's on the right side. So we want the negative symbol in this case. So we enter. So we should get, again, let's round to 3 decimal places, 9.507. But what is this? What were we solving for? How long it will take to decay to 100 milligrams. All right, so since our unit of decay is in 1,000 years, so our answer is 9.507 thousand years. To decay to 100 milligrams. And so this is actually pretty neat. Now, if I remember correctly, you guys are all geniuses at chemistry, correct? This is true? I'm not even going to wait for chat. I'm just going to assume it is true. So you guys are all amazing at chemistry. So you know that Aiden says, God, yes. Okay, so see, yeah, I knew it. So you guys already know that carbon-14 is what's called a radioactive isotope, right? You guys know what isotopes are. I'm not even going to pretend that you don't. And so isotopes, this is actually something that's really, really useful to us in real life. You know, like when you go to, you know, I don't know, either you're watching something or you go to a museum or something, and there's some artifact that's, who knows, like a tool or something. And they're like, yes, this stone tool was created 45,000 years ago. Or yes, this leather shoe was this artifact is 300,000 years old or whatever. And you're sitting there, you go, well, how the hell do they know that? They know that because they use this formula, right? They are able to, they know the rates that certain things should decay. So they can measure how much is left right now. Okay, how much was it? How long ago then was this made? And they can calculate. So for example, like we found a tea 9.5 thousand years ago. So sort of a similar style. So radioactive isotopes, whether we find like artifacts or when we find like, you know, mummies or skeletons or, you know, things like that, bones, we figure out how old they are because of this formula, the radioactive decay, the growth and decay formula. This is exactly what the solving does. Sorry, I got to play hooky and got to skip, not because of chemistry, but because I want Dairy Queen. Is Dairy Queen still open? There's no way, right? I refuse to believe that Dairy Queen is open right now. Oh yeah, I guess a lot of drive-throughs are. I don't know, but I've seen a lot of drive-throughs that aren't open. Like just it's the places are just closed down in general. I don't know, but yes, you should definitely risk you, your families, and the people's at Dairy Queen's health and well-being because you need to go get whatever you need from Dairy Queen. You dork. Okay. I think it's, hey. So, population of snail bots on the planet Dorberon grows at a rate of 4.1% per year. Currently, the population is 4,000. So part A, how many snail bots will there be after 3 years? Part B, how long will it take the snail bot population to reach 7,500? All right. So let's first just write our stuff, make our equation. It's growing at a rate of 4.1. So K is 0.041. It should be positive because it's growing. Current population is 4,000. So my growth rate model is 4,000 E 0.041 times T. That's just the general formula that I'm going to be using to work through this. So part A, how many snail bots will there be after 3 years? So I'm just going to plug in 3. So 4,000 e to the power of 0.041 times 3. Point 538. Snail bots after 3 years. Okay, I don't need to tell you guys how devastating a population of 4,523 snail bots could be. All right, we wouldn't stand a chance. And part B, how long will it take for the snailbot population to reach 7,500? Okay, so this is like our last slide that we did. So I'm going to take my formula, 4000 E 0.041 T. I'm going to set it equal to 7,500 because that's what the question's asking is how long will it take to reach this amount? Move it over so I don't have to move the calculator back. Again, we're not plugging in 7,500. We're setting the equation equal to 7,500. That way we can solve for t, figure out how much time. So we solve. Divide, oops, not 400, 4,000. Divide 4,000 on both sides. We have E that we want to get rid of. So let's use natural log on both sides. Oops, so that would get rid of the E, sorry. 0.041 times T equals and then lastly divide both sides by 0.041. And calculate. Let's see. Alpha y equals, to make the fraction, natural log 7,500 divided by 4,000, 0.041. Right, all of it entered together at once. $15.332. Right, see, it goes 3319, so that 9 rounds the 1 up to a 2 since we round to 3 decimal places. And what does this represent? We're talking about years. Right, that growth rate is in years per year. So this T so take 15, a little over 15 years to reach a snailbot population of 7,500, which again, I don't need to tell you how utterly horrifying that is. I mean, you thought viruses were bad. Well, just imagine 7,500 snailbots roaming your planet. It's just not going to go well. I'll never sleep again. I completely agree, Aiden. I completely agree. You know, life's tough when you grow up and you got to start thinking about adult problems like snail bots, and it's sad. You lose that childhood innocence. When we do solving these problems, they're pretty much, if we're solving for T or solving for K, we pretty much use the same process of solving. So it's going to be pretty common that, not immediately, but that I start going from this step right to here. Because eventually, after enough repetition, and we start to think about, okay, we know the steps. We divide 4,000, use natural log, divide by 0.041. It'll become much more second nature that you realize those middle steps you don't 100% need to write every single time. I mean, if you do want to, and if you need to, that's great, fine, do it. But I'm not going to, as we get more comfortable with this, I'm not going to spend as much time writing out all of that work that's in between. Okay. Last one. Let me move my calculator. (165 grams of magnesium 27, another isotope. After 9.45 minutes, there is only half the amount left, 82.5 grams. What is the rate of decay of magnesium 27? Okay. So initially, 165 grams. K. I don't know. Right, this is the first problem we've dealt with that I haven't been told specifically what the rate of decay is. Okay, so interesting. But the other thing that I do know is that after 9.45 minutes, there's 82.5 grams left. So whatever my equation is, if I plug in 9.45, I know that the answer I should get is 82.5. So that's helpful, I think. But first, let me just write the general equation as much as I can. So A of t equals 165 e to the power of k. I don't know what k is. And t. All right, so much less information initially in terms of the actual model because I don't know k. But that's all right because I don't know what k is, but I know this information, that after 9.45 minutes, there will be 82.5. So I know that if I take, nope, let's use red, this equation, and I plug in 5, not 5, where did I just get 5 from? 9.45, aha. I know that if I plug in 9.45, then it should be equal to 82.5. Right, that's what the problem, that's what the all that wording was told me. This is how much is left, 82.5. Well, how long did it take to get there? Well, it took 9.45 minutes. So plug in 9.45 for t, set that equation equal to 82.5, and we solve. So first, divide by 165. We need to get rid of the e, so we use natural log. All that's left is 9.45k equals all this garbage. So solve for k, just divide by 9.45. And then finally, substitute that all in. Alpha y equals, to make the fraction, natural log 82.5, 165. The denominator, 9.45. Now I'll reiterate. You don't have to use the alpha y equals to make the actual fraction. You can just use the division symbol. But when you do that, you have to be very careful about, you have to use parentheses because the calculator needs to know what exactly should be in the fraction and just that stuff. Otherwise, it'll start to think that other stuff is part of the fraction too. So I like using the alpha y equals because I can clearly see on my calculator screen that this is what I actually want to type in. I can match it exactly to what I wrote on my paper, my screen, and know that that is correct. I didn't know about this feature in my calculator when I was in high school doing math because I don't think any of my teachers knew that it existed either. And whenever someone showed me how to do this in college, I think I almost cried. Especially when you have ugly things like this where it's a fraction inside of a logarithm, which is inside of another fraction. So I just say better safe than sorry. Is go ahead and use it. That way you don't have to second guess like, did I mess up a parentheses or did I, so just take the worry out of it. But equals negative 0.073. 0.073. I'm going to real quickly ask myself, does it make sense that it's a negative answer? Okay. And yes, it should make sense because this problem is talking about decay. The amount of the magnesium 27 is decreasing. So our rate of decay should be negative. It makes sense. If I'd gotten a positive answer here at the end, I would be like, whoa, I messed something up. Dang it. But I got a negative answer, which makes sense because it should be negative. K should be a negative value when we're talking about things decaying. So let me actually put this in some context. So this is decays at a rate of 7.3% per, what are our units? Minutes per minute. So here's my final answer. Whew, went pretty long today, right up to the minute. So any last questions? I'm pretty sure that hold on, let me check. Yeah, I sent you a homework assignment with this. It's just practice with solving exponential equations and with solving some basic growth and decay problems like this. So it's not anything too wild, but just some various practice problems of doing that. So feel free to go through, try them out. If you have questions about them, if you try them out now for the next hour and a half or a couple, and then come back to my office hour stream at 1:45 and ask or email me questions or whatever. Again, you don't need to, I'm not collecting this in any way. You don't have to take pictures and email it to me, but please do still try to do some practice because at the end of the day, you still have to do PFAs and you still have to do performance tasks, whatever those look like. But so you gotta know how to do this stuff. But I guess if there's nothing else at the moment, I'm going to go ahead and log off for a second so I can get ready for my math analysis coming up soon. But I hope you guys are doing well. Again, as always, super appreciate being here and watching and asking questions and stuff. It's awesome. I really appreciate it. And it's good to be able to interact with you guys. So thank you. You're awesome. All right. Have fun. Have a great rest of your day.